Hello everyone, my name is Wicked New. You can also call me Evan. I'm currently a research fellow under Professor Kai Kit Wong at the Department of Electronic and Electrical Engineering, University College London. And our research group is working extensively on the topic fluid antenna system. So in this tutorial, I will talk about MIMO-FAS, where MIMO here represents multiple input, multiple output, and that is a multiple antenna wireless communication system, and FAS here represents fluid antenna system. Okay. So this is the outline of my tutorial. So firstly, I will introduce you to MIMO-FAS. Next, I will talk about the degrees of freedom in MIMO-FAS. Now, compared to the conventional definition, the degrees of freedom here refers to the one in the system rather than the one in the received signal space. And then after that, I will discuss about the diversity and multiplexing trade-off of MIMO-FAS. In particular, this to show the superiority of MIMO-FAS as compared to traditional MIMO system. And furthermore, I would also like to share some very interesting results, such as simultaneously achieving full area gain and no stirring, as well as strong channel hardening, which were discovered by some of the very bright researchers in the world. I believe these are very interesting findings because they showcase the unique features of MIMO-FAS. Okay, so at the end of this tutorial, I hope that you understand what MIMO-FAS is, and I believe that you will be able to witness the theoretical superiority of MIMO-FAS as compared to traditional MIMO system, and also learn the unique features of MIMO-FAS. Okay, so let me introduce you to MIMO-FAS. Firstly, what is FAS? So FAS may represent a system where the position of the radiating elements can be dynamically reconfigured. For example, in liquid-based antenna, the droplet or metal liquid can be switched to a specific position, or we call it port. Okay, and in pixel-based antenna, this means that any of the NS pixels or the ports can be activated. All right. So what is MIMO-FAS? Well, MIMO-FAS refers to a FAS where multiple ports can be activated. For example, NT ports can be activated at the transmitter side, and NR ports can be activated at the receiver sides. Okay, so each of these active ports is flexibly connected to a RF chain. And in liquid-based antenna or pixel-based antenna, this can be achieved by using surface wave technology. Okay. Furthermore, it's worth mentioning that when both of the transmitter and receivers are equipped with fluid antenna, we refer to such system as the dual MIMO-FAS. Now, when the transmitter is equipped with fluid antennas and the receiver is equipped with traditional antenna, we will refer to such system as TX MIMO-FAS or transmit MIMO-FAS. And conversely, when the receiver is equipped with fluid antenna and the transmitter has traditional antennas, we refer to such system as the received MIMO-FAS or RX MIMO-FAS. Okay, so what is the additional degrees of freedom in MIMO-FAS? The additional degrees of freedom in MIMO-FAS is the very precise position reconfiguration of the active radiating elements, where the precision can be much smaller or finer as compared to half a wavelength. Okay, and with this additional degree of freedom, MIMO-FAS can jointly optimize the active parts, beamforming, and also power location. So when optimizing a function with respect to these variables, this usually yields a non-convex optimization problem, right? In fact, when the parts are discrete, this usually leads to a NP-hard problem. So to solve this optimization problem, what one can do is that perhaps one can look at alternating optimization technique, convex relaxation, parallelity methods, machine learning methods, and so on. All right. But at high SNR, it is possible to actually use strong rank revealing QR factorization, SVD, and eco publication to obtain a very efficient or near optimal result, perhaps as a benchmark. Okay. So every MIMO system has a fundamental trade-off between diversity gain and multiplexing gain. All right. For example, when some of the antenna are used for multiplexing gain, then this antenna cannot be used for diversity gain. And conversely, when the remaining antenna are not used for multiplexing gain, then it is more efficient or optimal to actually use for diversity gain. And therefore, there's this fundamental trade-off. So this trade-off is referred to as the diversity and multiplexing trade-off. Okay, so in particular, when a system is said to achieve a multiplexing gain of R and a diversity gain of DR, when the rate scales like R log SNR and the outage probability scales like SNR to the power of negative DR as SNR approaches infinity. Okay, so since every MIMO system has this trade-off, then this DMT becomes a very suitable metric to evaluate the performance of different MIMO systems. Okay, so let us look at the DMT of MIMO and MIMO-FAS. So this figure here shows the DMT of dual MIMO-FAS, TXRX MIMO-FAS, and also MIMO. And as you can see in this figure, the DMT of MIMO-FAS is an outer bound to that of MIMO, right? Specifically, the maximum multiplexing gain of both this scheme remains quite similar, but it's worth noting that the rate of MIMO-FAS is slightly higher than that of MIMO. It's just that the rate doesn't scale like with respect to the SNR, and therefore it doesn't consider as a multiplexing gain. I mean, in fact, there's insufficient resolution as well. Nevertheless, the maximum diversity gain of MIMO-FAS can be significantly higher than that of MIMO. For example, as shown in this figure here, the maximum diversity gain of the MIMO-FAS is M prime Rx as a function of WRX times M prime TX as a function of WTX. And this actually represents the number of significant part as a function of the surface area. Okay, so to get a rough idea of how much diversity gain can be obtained, we can rely on numerical approximation. And this numerical approximation actually represents the non-trivial eigenvalues that can be used to improve the diversity gain. Okay, so for example, if we consider a surface area of half a lambda times half a lambda, half a wavelength times half a wavelength, sorry, then the maximum diversity gain of MIMO-FAS can be 169, while the maximum diversity gain of MIMO is only 16, assuming that the antennas should be separated by at least half a wavelength in MIMO. Okay, now as the surface area increases, of course the diversity gain also increases for both schemes. And ultimately, MIMO-FAS is still much more superior than MIMO. So from this result, it's obvious that MIMO-FAS has a significant advantage in terms of diversity. And this is because in order for MIMO-FAS to have an outage, all of these spots needs to experience deep fading. Okay, so these slides here, especially this figure, really shows the superiority of MIMO-FAS as compared to traditional MIMO. And next, I would like to share some very interesting results. So one of the results is that MIMO-FAS can achieve full area gain and no slurring, and this is discovered by reference through here. Okay, so to see this, let us consider a finite scaling environment, and also let us consider a specific realization where the desired direction is 90 degrees, and the interference direction are 30, 82, and 100 degree. Okay, so due to the fixed position of the radiating elements, it can be shown that MIMO-TAS cannot achieve full array gain while no steering the interference direction. Okay, but MIMO-FAS can actually concurrently achieve full array gain and no steering, and this because the position of the radiating elements can be reconfigured. Okay, so what this suggests is that MIMO-FAS can actually provide a higher channel to interference ratio. Okay, so next is that reference tree here, Cheng, actually shows that MIMO-FAS can achieve strong channel hardening with significantly fewer active radiating elements as compared to MIMO-TAS. Okay, so compared to MIMO-TAS that relies on law of large number in massive MIMO, MIMO-FAS here actually exploits the extreme value theorem to realize strong channel hardening, and thus it requires much fewer active radiating elements. For example, to achieve a 0.05 channel variation, MIMO-FAS only requires 20 preset location, okay, while MIMO-TAS here needs 170 antennas. So you can see that the performance of MIMO-FAS is significantly much better, and this could improve the spectral efficiency and energy efficiency. Okay, so this sums up our tutorial. I hope that you enjoy my sharing. And if you'd like to know more about fluid antenna system, feel free to also visit this website here, www.eeucl.ac.uk, fluid antenna system. And with that, I thank you for your time. I hope you have a nice day. Thank you.